Morning, everyone. My name is Aris, and today I will be speaking to you about whether machines can think like people. Or rather, I'm going to be talking about some of the things that we found in artificial intelligence and how they relate to the way that humans think. So firstly, we're going to talk about some impressive recent achievements that people have been excited about, and later on we're going to talk about how they relate to human thinking. So firstly, Google's recently released a pathways language model, which is similar to other large language models that you may have heard of, like GPT and so on. One of the things people were very surprised and impressed by was that it can explain a joke. So if you say, explain this joke, and you give it the problem with kleptomaniacs is that they always take things literally. It's able to tell that this joke is wordplay, and it can explain how it works. It's even able to tell when something is an anti-joke and isn't actually meant to be funny, but the joke is on you, rather. It can write code based on prompts. It can do maths that it wasn't taught to do, like it was just read in some of the text it was given that 2 + 2 is equal to 4, and now it knows that 4 + 4 is equal to 8. So people have been very excited about that. Another one that's been making it big on social media is Imagen, which is more new, and Dolly 2, which if you give it a text description, they generate images for you. So for example, you tell it that a brain riding a rocket ship is heading towards the moon, and it gives you this picture, and so on. So these are the examples from Imagen, and this is from Dolly 2. So for example, if you tell it, I think this was the 2 teddy bears doing mad science in steampunk style, or a fox sitting in the sun in the style of Monet, and it can generate novel artwork. So it can both understand the prompt that you're giving it and generate images of things that it hasn't actually seen. These aren't really very new, but AlphaGo and AlphaGo Zero and their successors were quite a big deal when they came out. We thought that Go was a really hard game, and we were all struggling to try to get AIs to beat humans. And then finally, AlphaGo beat the human champion. And then it was followed by AlphaGo Zero, and then AlphaZero, and then MuZero, which doesn't receive. So AlphaGo was taught how to play Go. So the future ones weren't given the rules of Go. They weren't given human games to watch. They weren't given anything. They were just told, okay, now you play against yourself, and when you get points, you'll get points. And then they ultimately outperformed AlphaGo, and now I think MuZero can also play chess and multiple other games just based on teaching itself. More recently, we've had another approach to creating a generalist agent. It's also based on a similar approach to large language models, which is to say, with a language model, you get a set of tokens and you try to predict the next one. So the idea is that you can present all sorts of other tasks as a sequence of tokens for you to predict the next one, where the next one might be an action that you take, a move that you make in a game, or whatever else. So they trained it on all sorts of things. Text generation, labeling images, playing all sorts of games, even moving a robotic arm to stack blocks in the order you say. And it's a lot smaller than such models usually are, and it performs really well. Normally what happens is if you try to train a model on a number of different things, it sort of gets confused in a way, so it performs less well than one that you train on one specific task to be an expert in this one. And that's not really the case with Gato. So people are very excited that if we make it bigger, it's going to do amazing things. So how does this relate to humans and how we think? So first of all, you might know that the initial idea of neural networks is based on an abstraction from how the brain and neurons in the brain work. So you get these dendrites, you have a previous neuron somewhere here, and it's firing you neurotransmitters to each of these receptors. Some of these might be stronger than others, some of these might be negative, and so on. And then in here, it combines all of these signals, and it generates an electrical impulse that's sent through to the next one. Similarly, with the artificial neuron, it gets all of these inputs. Some of these might be weighted more than others, some of them might be bigger, smaller, etc. It combines them using some function, and it sends them through to the next layer, and so on. So obviously, all of these results that I've been talking about use neural networks, I think. Then reinforcement learning. You may have heard of Pavlov's dogs, where Pavlov rings a little bell and gives his dogs food, and he keeps doing that over and over, and eventually he can just ring the bell and doesn't give his food, and the dog still salivates because it thinks that it's getting food. And there's a more broad version of this where basically you learn by getting rewards for good things and punishments for bad things. So you learn to do the good things and not do the bad things. Reinforcement learning is based on this idea. So you get this agent and it gets some information about the world and what state it's in at the moment. It takes some action that changes the state of the world and gives it some reward or negative reward. Based on that, it learns what actions it should take and not to take to maximize reward. So one of the ways that reinforcement learning works in the brain is using dopamine. You may have heard it considered the reward chemical, that you get dopamine when you eat, you get dopamine when you do this, but it does all sorts of other things across the entirety of the brain. So one of the ideas is that it also rewards learning by making correct predictions. So if you say, if you believe that if I hold out this ball now and I drop it, it's going to go up, then when you drop it and it goes down, then your brain punishes you because you were wrong about how things were. And using that, it corrects itself so that you believe true things and you learn about how the world works. In fact, the part where you enjoy things, where dopamine creates enjoyment, is also very much based in the predicting of the enjoyment more so than the actual enjoyment. For example, in some conditions like schizophrenia, where people have anhedonia and they can't experience pleasure, what we find is that if you actually give them, like, I don't know, a chocolate cake, the brain response is not different to people who are experiencing the pleasure. The difference really is that they don't expect to enjoy it, and then they don't. So this was implemented in temporal difference learning algorithms, where rather than, normally they try to predict how much reward they'll get overall, and using that, it decides, okay, if I take this action, my overall reward will look like this. If I take this action, my overall reward would look like that, and decides which one to take. With temporal difference learning, instead of trying to predict its reward, it tries to predict what it will next be predicting to get a reward. And that also is quite successful. And then we have predictive coding. So this is a model of how humans perceive, they do sensory perception. For a very long time, it was thought that, like, you just take your raw sensory input, all the lights and the signals that you get in your eyes, and you take them and you process them, and from that you get an image. And what predictive coding says is that actually you start with a mental concept of what you think is going to be there, and then you get these sensory inputs and you adjust your expectations and according to the error from what you're actually receiving. So you're sort of creating what you see in a way. So this kind of concept has been applied directly in reinforcement learning, in robotics especially, in some ways. In an indirect way, the idea of backpropagation in neural networks is somewhat similar. So it gets this result, and then it goes back and tries to adjust how it was doing things so that it gets a better result. And if we look at deep convolutional neural networks that are often used for object detection in images, they show pretty similar patterns to how the human visual system works in the brain. So that's very good for sensory perception. It's the generally accepted model for sensory perception. But what else can we apply this prediction model to? So a generalization of the predictive coding model is the predictive processing model. It says that all of your brain, your entire brain, is a prediction engine. All of your thoughts are somehow related to predicting things. So the large language models we were talking about earlier, the transformer models, one of the ways you train them is by predicting the next word. So you give it a sentence and you hide the last part, and it tries to predict what the next word would be. And so recently they did some research also similarly to how they looked at deep neural networks, comparing them to visual networks. So they looked at models that are predicting the next word in a sequence. They're also better at predicting how the brain would respond to the same sequence in predicting the next word. So there is evidence that human language processing works similarly to the predictive processing in neural networks. I don't know if you guys have heard about the Google engineer a few weeks ago who has been arguing that their chatbot is sentient and has apparently been placed on administrative leave for this. Anyway, moving forward, there are also important differences between how machines and neural networks work and how humans think. Modern machine learning tends to focus on finding statistical correlations. So basically it uses heuristics and search, but a lot of human cognition is based in mental models that you use, and you use them to explicitly reason about premises and conclusions using logic. Causality plays a very big role in how we think about the world. And because we do a lot more explicit reasoning, we're better able to explain and communicate what we're concluding. If you know about system 1 versus system 2, this could kind of be thought of like that. So system 1 is your fast, immediate processing, where you just sort of implicitly, intuitively conclude things, and you can think of neural networks as doing something like that, versus system 2, where you think through how the steps and everything works, come to a conclusion based on logic. Also, humans are few-shot learners, so to say, which is to say we don't need massive amounts of data. We can learn new things from fairly limited exposure. Now, we've asked if they can, but did we ever stop to think if they should? There was supposed to be a very dramatic animation here. Unfortunately, this is absent, but yes. So obviously, we need to think about this. So there are some considerations. AI safety is, of course, a big one, but you guys probably already know about that, so I'm not really going to go into that. But on the other hand, maybe machine intelligence can be better by not trying to emulate humans. So some researchers think that we would have to add like the explicit reasoning kind of approach to cognition to machine intelligence in order for it to be as intelligent as humans. But some researchers say that, why are we trying to emulate humans? Maybe machines have different advantages and disadvantages, and we should take advantage of that because we can make them really, really big, and brains have limited capacity and have to work within that capacity. So instead of trying to focus on emulating humans, we should try to focus on things that can take advantage of increasing computation. But at the same time, interfacing with how humans think is essential for being able to communicate and explain between machine learning models and humans. And as machine learning becomes increasingly prevalent in society, taking bigger and bigger decisions for us, it's more and more important that we are able to do that. So being able to understand how it works is useful. That's all. Thank you very much.